Hey guys, it's Sunny again. Had a couple things to tag on to our last video. I just wanted to include those here. And by the way, both of these videos are coming from the information that's in chapter 2 of your book. If you haven't looked at that, read that and follow along that. You'll learn a lot more about electromagnetic radiation. By the way, electromagnetic radiation is a natural part of the environment, and it spans a large continuum of ranges in magnitude of energy. This is a picture of what we call the electromagnetic spectrum. All the way from the left to the right, we see gamma rays on the left, we see AM radio all the way over here on the right. The further we go to the right, the longer these wavelengths are, and as a result, the shorter, or the lower the frequency, I should say. And you'll see, just for reference, this colorful bar down here at the bottom is our visible light spectrum, which is actually broken out and amplified or magnified. It comes from this little sliver right here of the electromagnetic spectrum, right near the middle. So it might interest you to know, if you didn't, that the visible light that we can actually see is an extremely small part of the electromagnetic spectrum. Just to the right of that, we see infrared rays, which is light, just like the light we can see. The only difference is our eyes can't pick it up. It is no different than the visible light, except that our eyes just are not sensitive to it. But notice that the infrared spectrum here, or infrared part of the spectrum, is many, many times larger than the visible spectrum. And the same for the ultraviolet side. On the other side is many times larger than the visible light, and it is light as well. So if we look from ultraviolet through the visible and the infrared, we see that light makes up this part of the spectrum right here. To the right of that, a little bit longer waves, again shorter or smaller frequency, is radar, and then we see FM radio, TV, shortwave, and then AM radio all the way to the right. What we're interested in right now is to the left of the ultraviolet, we see the X-ray part of the spectrum, and it's very large. It's almost as large as the entire light spectrum combined. So this is where we generate our X-rays from. X-rays are very, very short wavelength, very high frequency. As a matter of fact, we'll find out that the higher the frequency, the stronger the X-ray energy is. So as we go to the left on this, we get stronger and stronger X-rays. And then to the left of that, we see gamma rays. You've heard of gamma rays. Gamma rays and X-rays are both used in medical imaging, obviously X-ray energy for developing images, but gamma radiation is also used in the nuclear medicine studies that you've heard about. If you recall, we mentioned the isotopes a little bit earlier. Isotopes are where basically a neutron is removed from the nucleus of an atom. That is done with an injection of radio medicine that emits those, and those are emitted from the body, picked up by a gamma camera, and then displayed on an image intensifier, so a physician can look at that and tell whether or not possibly you have something going on with your tissue there. So gamma rays are what we use for nuclear medicine studies. We'll talk about that a little bit more, but we're going to focus most of our time and energy on this X-ray portion of the spectrum here, because that's what this is primarily, this course is about. So again, X-rays are part of the electromagnetic spectrum. Not that much different really from the rest of the electromagnetic spectrum, except in frequency and wavelength. Okay, so what is EMR, electromagnetic radiation? Actually, it asks the question here, which is not an example of electromagnetic radiation? And we've got 4 here: electricity, visible light, radio, TV signals, and visible light. And we can remember, we had this discussion, visible light is obviously on that spectrum we saw earlier. So were radio and TV signals and the invisible, ultraviolet and infrared portion of the spectrum. So these 3 are in the electromagnetic spectrum, which leaves electricity as the odd man out. So electricity is not part of the electromagnetic spectrum. And in fact, if you think about it, these other three are transmittable. They can actually travel through space. We can't do that much transmitting of electricity through space. I know lightning can do that, but that's a rare example. So electricity would be the answer to that question. There's been some question about whether electromagnetic radiation is a wave of energy or particle of energy. So that's what we're going to talk about in just a minute here. The wave theory of electromagnetic radiation basically says that it has a wave-like properties to it, and we know that it does because we talked about the wavelength, we talked about the frequency. Those are things that are associated with wave theory. Also, we see here that the frequency is measured in hertz. And the wavelength is also something that we can measure. So obviously it has a wave particle to it. Then we have a particle associated with it too. Is it a particle? Well, who knows? There's been some discussion about that. And so they're saying it has quanta or photons. It has discrete packets of energy that we call photons or quanta. So it has some of the elements of a particle associated with it. It has energy levels associated with it. And so the answer to that question is basically it is both. It's a combination of the two. It's electromagnetic energy is best described as combining the properties of wave and particle theory. It has a frequency, it has a wavelength, and it behaves like a bundle of energy or particle that we call a photon. And you've heard that term photon, I'm sure, if you watched any of the Star Trek shows, and really, that's what it is. It's particles of energy that are transmitted to do some kind of work. The nature of ionizing radiation, again, it can be positively or negatively charged, depending on how it's interacted with. It has the ability to affect various organs and tissues in the body, and it's capable of displacing atomic electron bonds and breaking the electron bonds that hold molecules together, which results in chemical changes, which in turn can lead to harmful effects in the body. Again, that's why ionizing radiation is dangerous to the body, because it can have an effect on the chemical and the physical tissue if exposed to it long enough. So we have to understand the safety precautions associated with that too, and that's going to be a big part of what we study in here as well. So we'll see that actually toward the end of this part of the semester. We'll talk about radiation safety a little bit more. Just one more or two more slides here. This is a short video, but X-rays and gamma rays. X-rays and gamma rays are essentially the same except for the origin. Again, gamma rays are emitted from the nuclei of radioactive materials. I said earlier, nuclear medicine emits gamma rays, which are basically emitted from the body or from the tissues of the body and picked up by a gamma camera. And the X-rays are man-made with an X-ray tube with a high impact electron collision generated at about 150,000 volts. So we're going to talk about that a lot. We're going to get into that real soon about how we actually generate this X-ray energy with this equipment. And the next thing we want to take a look at is how the equipment that we actually do with that. It's actually a room full of equipment that's associated with this, but it all boils down to the generation of the X-ray energy, which is taking place in the X-ray tube itself. And I'll show you some better pictures of that, some actual, some illustrations of an actual X-ray tube. This is just sort of a block diagram of what's going on in there. I will tell you this, you'll see here, we mentioned earlier that this is generated at about 150,000 volts. If we look at this, we'll see up here at the top of this X-ray tube is a negative 75,000 volts. Down here at the bottom, we see a positive 75. So the difference in negative 75 and a positive 75 is 150,000 volts. So we're applying 150,000 volts across this X-ray tube, and then we have some other elements that are in here, and I can explain. I am going to explain those to you, but I'm going to leave you with this. You see, this is numbered here, and I didn't put everything in here, but what I'm going to ask you to do is go to chapter 6 in your book and look up what these elemental parts of this X-ray tube are. That'll be the best way, I think, for you to understand this, because this will be definitely on a test. It's not very difficult at all. But how this thing actually works is really fascinating. So we're going to talk about that in some detail in upcoming videos. But for now, that's it. Again, take a look at Chapter 6 just to, the rest of this video was in Chapter 2, but this X-ray tube I think you'll find in Chapter 6, where you can actually find the component parts of this. Record those. I'll probably put an assignment on Moodle for you to upload this to me, so I can see that you actually understand what's going on here. One more thing, if you want to do it, you don't have to do this. This is actually for a little bit later. I do have an address to an X-ray simulator on here that you can copy and paste into your browser and play around with. It's basically a simulator of X-ray energy. You can see what the effects of some of those things are. It's a little premature. We haven't got to that point yet. But if you want to play with it, that's fine. But we'll come back to that a little bit later. For now, take a look at that X-ray tube and see what those parts are. Talk to you later.